Hello. Today we will be tackling shortest paths. I am Kenisha Muse, and we will be discussing Dijkstra's algorithm, the traveling salesman problem, and the Chinese postman problem. So let's start. Firstly, with Dijkstra's algorithm. Dijkstra's algorithm, named after computer scientist Edgar Dijkstra, is designed to find the shortest path between nodes in a graph. It's widely used in network routing, geographical mapping, and even in game development. So before we head on to our example, let's break down the algorithm. Imagine we have a graph with nodes connected by edges. Each edge has a weight, representing the cost or distance between the nodes. Starting from our initial node, Dijkstra's algorithm explores all neighboring nodes, calculating the tentative shortest path to each. We then select the node with the smallest tentative distance, mark it as visited, and repeat the process until we reach the target node or explored all nodes. Now let's have an example. I'm going to teach you how to run Dijkstra's algorithm on a weighted directed graph. Again, Dijkstra's algorithm tells you the shortest distance from one node to every other node in the graph. This differs from Prim's and Kruskal's, which result in minimum spanning trees. So let's use the following graph for our example. We'll keep a list of unvisited nodes at the bottom. Our first step is to pick a starting node. Let's choose A. We'll use the table on the right to keep track of distances. Remember, the distances we are measuring are from our starting node A. We put 0 for A and infinity for the others as we haven't visited them yet. The next step is to examine the edges leaving A. We can reach B and C from A, so let's update the chart with the corresponding cost. Next, we look at the chart and pick the smallest edge of which the vertex hasn't been chosen. In this case, C. So let's cross off C in the unvisited node, marking it as closed. After choosing C, we examine the edges, leaving C, and update the chart accordingly. B is now reachable from A with the cost of 3. By traveling through B, D and E become reachable for the first time. Let's do the same thing as before and choosing the smallest path with a node closed node, this time B. We repeat the process examining the edges, leaving B, and updating the cost, getting to D and E. Now we choose D this time. This time there are no updates to our table as there are no edges leaving D. Finally, we choose E. Again, there are no updates this time because the edge leaving E does not result in a shorter path. All the edges in the graph have now been visited and are closed. So here is the shortest path from A to the other nodes. So in summary, Dijkstra's algorithm is a powerful method for finding the shortest path in various applications. Next, we will be tackling the traveling salesman problem. Moving on to the traveling salesman problem. The traveling salesman problem, or TSP, asks a simple question. Given a list of cities and the distance between each pair, what is the shortest possible route that visits each city once and returns to the origin city? TSP is an NP-hard problem, meaning it's computationally intensive to solve exactly, especially as the number of cities grows. Finding the optimal solution requires evaluating all possible routes, which becomes impractical very quickly. To tackle TSP in practice, we often use heuristic methods. The nearest neighbor algorithm is a simple approach. Start at a city, visit the nearest unvisited city, and repeat. Though it doesn't guarantee the shortest path, it's computationally efficient. Genetic algorithms mimic natural selection to find good solutions over iterations. These methods involve creating a population of roots, evaluating their lengths, and iteratively combining and mutating them to find shorter paths. TSP solutions are crucial in logistics, like route planning for delivery services. By using heuristic methods, companies can significantly reduce travel time and cost, improving efficiency. Now let's have our example. Sheldon lives at A. He wants to visit B, C, D, and E before returning to A. Let's find the upper and lower bounds. So first, let's find the upper bounds using the nearest neighbor algorithm. So for the nearest neighbor algorithm, we first start at an arbitrary city. So let's start at city A. So let's visit the nearest unvisited city. Between 16, 22, and 15, it looks like our nearest city is D with 15. So let's repeat that until we reach all the cities and go back to A. So 15, 7, 4, 18, 19. A, D, E, B, C, D, and back to A. Adding the sum of all the nodes, we get 76, which will be our upper bounds. So to find our lower bounds this time, we actually have to eliminate one node, or one city rather. It doesn't really matter which city you eliminate, but I chose to eliminate city C. So now we are left with A, B, E, and D. And from B, we need to find the shortest route going back to A. So, which is BE 4, ED 7, AD 14, which is equal to 25, which is not actually our lower bounds. It is our minimum spanning tree. And now adding 18 and 19 from city C, we now have 62, which is our lower bounds. So now we can conclude that our optimal route rather, um, is less than or equal to 76, but greater than or equal to 62. So in conclusion, while the traveling salesman problem is very complex and we were only able to solve a very simple example, heuristic methods provide practical solutions. And next, we will be tackling our last topic, which is the Chinese postman problem. The Chinese postman problem, or CCP, or CPP, sorry, aims to find the shortest closed path that visits every edge of a graph at least once. It's named after the task of a mail carrier delivering letters along a specific route. CPP is related to Eulerian paths, which traverse each edge exactly once. If a graph has a Eulerian circuit, solving CPP is straightforward. However, most real-world graphs require some edges to be traversed more than once. To solve CPP on a non-Eulerian graph, we transform the graph by adding edges to make all vertices have even degrees, creating a Eulerian circuit. This process ensures every edge is covered efficiently. Now onto our example. Remember, you have to deliver to every house and get back to A in least time possible. So let's pretend that these letters are houses and these numbers denoted the distance between them. The first step is to find the total weight. This can be done by simply calculating the sum of all the numbers here, which brings us to our sum 53, our tentative total weight. Next, we have to figure out all the vertices with an odd number of edges. So as you can see, we have concluded that B, C, G, and F have an odd number of edges with 3 edges here. Next, we have to make all possible sets of pairs of nodes, GBFC, GFBC, and GCBF. And then we have to choose the pair with the least cost, which is obviously GF and BC with only 7 total, if you add their 4 and C here. So then you add that cost to the previously calculated cost, hence bringing us to our final total cost of 60. Thus, The optimal route for this, assuming that these two have been connected, is from A to B to G to F to C to B, then back to C to D to E to F, then to G, and then back to A. So that's all for this lesson. Thank you. And I hope that you enjoyed and learned as well. Thank you so much again.